quickly introduce Heather. So Heather Stoll, probably most of you know her already. Heather Stoll is today a full professor and the head of the climate geology group at ETH Zurich. And before being appointed at ETH, Heather was an assistant professor of geoscience at Williams College in Williamstown, USA, before being a professor in the department of the University of Oviedo, where she also received tenure in 2007. Heather's interests for understanding Earth's climate history are very broad. She works in both. She works in carbonate systems from the marine and the terrestrial realms, and also she works on multiple timescales spanning the last 10 million years up to the present. She comes with a very strong background in geochemistry, and she has developed a number of methodologies and uses various approaches ranging from experimental studies, such as calcite culturing or monitoring studies, up to more conceptual and mathematical modeling topics. From our perspective from SciSci, we think it's very exciting to have somebody here that is presenting with this very broad background and has a very broad conceptual understanding. And also from my personal experience, I think Heather is an amazing teacher, so we are really looking forward to this seminar. Take it on, Heather.
Thank you so much, Laura. And I hope I can live up to at least some of what you've promised here. So thanks to everybody for coming this morning online, at least we can be together to share some ideas. And I look forward to getting your feedback today. So the work I'll show is an ongoing collaboration with people in our group and elsewhere. And if you have questions to follow up, my email's on the first slide. You can always flip back to that for the recording. So the motivation I have for talking today about carbon isotopes and PCP is really twofold. So on the one hand, 15 years ago, I heard this talk by Tim Atkinson at a conference that really inspired me. And he was commenting that sometimes we go into a cave, we sample stalagmites that might even be right next to each other in the cave, and we measure their isotope records, and we expect that they should give the same signals. They're in the same environment, forming under the same climate. And we might expect their isotope records to be in unison, really essentially the same, like this example. But as Tim Atkinson pointed out, sometimes they are in harmony, so giving about the same trends, but a little bit offsets. But the most puzzling case is that there are times when we have multiple records from the same cave and they don't correlate at all. We can see that unison and harmony, we would get some correlation coefficient in these time series of stalagmites, isotopes. But in this last case, they don't correlate. What could be causing these isotope records in the same environment to look so different? And I'd like to talk today about whether PCP might be a significant factor that's taking a harmonious climate signal and transforming it into this chaos or cacophony. And the other motivation that I have is that, especially in the mid-latitude regions, there are many settings where the carbon isotope ratio of the stalagmite is not only controlled by PCP, and PCP might not even be the dominant control. Rather, the carbon isotope ratio of the CO2 in the epikarst above the cave really strongly imprints on the DIC and the stalagmite. And the consequence of this was noticed already 20 years ago in this nice figure from a paper by Dominique Gentil, where he pointed out that in Villars Cave on the Atlantic coast of France, the carbon isotope record, here shown in red, carried positive anomalies every time the Greenland ice core showed cold conditions. So he said that the carbon isotopes in the stalagmites in this environment are very sensitive to temperature. And there's been a very nice modeling study by Francie Lechtleitner showing why. We've done some further work over the last deglacial transition, looking in Northwest Iberia where the red star is, and comparing the carbon isotopes in the stalagmites over the last 25,000 years with independent temperature records from nearby ocean cores, and showing again that there's a strong correlation. And this is overall because when the temperature is warmer in this setting, it generates higher respiration rates and higher CO2 in the soils. So the respired component in the soils is pulling the isotopes negative. So it's possible that when CO2 is not limited by temperature, but rainfall, the PCP and the original soil epikarst signal might just enhance each other. But where temperature is driving the soil PCO2, it may not go in phase with PCP from rainfall limitation. Okay, sorry for the chaos in the laser pointer as I advance the slides. So the goals that I'd like to talk about today are, could we transform the carbon isotope cacophony or chaos into harmony by thinking about how the PCP is affecting the records? And at the same time, can we separate or deconvolve the parts of carbon isotope variation that are due to changes in the soil and the epikarst from those that are due to the in-cave PCP effects? And I'd like to do this in a way that gives everybody an easy tool, an Excel sheet, so that people can do sensitivity checks of their own stalagmites where you have trace element and carbon isotope records to see if this is relevant to your settings. And at this point, we don't have everything we need to do a perfect separation of these effects, but I hope that in presenting this today, we'll all start to think about what we can do in our various cave systems and labs to get some better understanding of the variables that we don't know so well. So the outline for what I'll do this morning, first, level 0, I'll give just a quick review of some things we often forget about PCP. And then the main essence is, can we quantitatively reconstruct PCP from fossil stalagmites? And we'll talk about that in the first half. And then if we know how much PCP we've had at different times in the past in the stalagmites, do we know how the carbon isotopes change with PCP well enough to apply a correction and separate these effects? And that will be the second part of the talk. Okay, so right away, let's go on to things that we knew about PCP but might forget. So we often think that PCP is controlled by the drip rate, and that is one factor. And when I talk about PCP, I'm really talking about degassing and PCP, and also the extent of precipitation that happens on the stalagmites. And the metric I'll use is this fraction of Ca, the fraction of initial calcium that was in the initial drip water that remains in solution at the end of the deposition of the growth layer. So an FCA of 1 means that you've had almost no calcium lost from the solution. And an FCA that's low, 0.2 or 0.3, means you've lost almost all the precipitable calcium from the solution. So in this case, degassing is going in this direction. So here I've plotted just for a simple scenario with Dripwater kinetics and temperature, that of course there's a relationship as you get longer and longer time interval between successive drips, there's more time for prior degassing. And so PCP increases or the fraction of calcium remaining goes down. But the important thing is this is not a linear relationship. And on the right, I've plotted the derivative just to show if you have a 50% increase in the drip interval, as we make the drips 50% slower, how much does that change the FCA? And we see that there's a point where it's very sensitive. And the peak of this curve may shift a little bit with temperature, but where drip intervals get into, say, hundreds of seconds, then changes in the drip interval make a big change in PCP. But if you have, even if you double the drip interval, if it's already very fast, it won't change PCP. So you could have a stalagmite growing with this kind of drip interval and a stalagmite growing with these, and they could record completely different PCP time histories. And that, I think, can introduce some of this chaos or cacophony when this is overprinted on the stalagmite records. Now, we often forget that the drip interval is not the only factor that can change the PCP. So this is just a simple simulation. In this case, I've used the exact same drip interval for all of these calculations, but I'm changing how oversaturated the drip is with respect to the cave. So what's the initial calcium concentration? And when you start with a lot of calcium in the solution and you have a long drip interval, you have time to degas a lot of it. And so you could degas, say, half of it in 300 seconds. Whereas if it starts with a much lower saturation in that same drip interval, you don't degas as large a fraction of the drip. And we could see this maybe a little bit better looking at the landscape. So if we imagine, under a forest where there's high CO2 in the soil and you dissolve a lot of bedrock, maybe you get up to 100 ppm calcium, and then you drip it into the cave, the saturation in the cave at cave temperature, cave CO2 might be 25 ppm. So you could lose up to 75% of your calcium before you hit that saturation limit. So you can have a pretty wide range of possible PCPs. Right. In contrast, if you have barely any soil, barely any CO2, you're not dissolving much calcium, maybe you only get 40 ppm out of the bedrock. When that enters the cave, if the saturation is still 25 ppm, you just don't have that far to go before you hit the saturation. So you can lose a much smaller fraction of your calcium. And consequently, the FCA, is this fraction of calcium remaining, is going to stay rather high. So this means that often for the same drip interval in a cold climate in the mid-latitudes, you'll have less PCP than you will in a warm one. So here's another graph just illustrating the possible range in FCA that you can get as a function of the initial calcium ppm. And I've just truncated this by saying if you get less than this, the growth rates are so slow, we wouldn't typically be working on those stalagmites. So this right-hand tail is the lower limit of FCA that you can get and still be growing calcite. So this is really leading to a couple of consequences. First, correcting records for temporal changes in PCP. It's actually going to be more important during interglacial times or during very warm climates. But it can also lead to competing effects, because when you have the highest soil CO2, that's when you're going to have the most negative initial carbon isotopes in the drip water. But it's also when that drip water is most prone to have a strong PCP overprint. And there may be stalagmites in a very sensitive range of drip water where those two factors come together and make it difficult to see both a PCP and a temperature signal because they're canceling out. So let's get into the meat of, can we do anything to separate these factors, and can we come up with some strategies to distinguish PCP and non-PCP effects? To do that, we first need to have a quantitative indicator for PCP. And here I'm showing two possibilities that I will use. On the left-hand side, I'm showing stable calcium isotopes, so the delta 44 to 40 calcium on the x-axis. And then what happens is that the lighter isotope of calcium dissolvates more quickly, and so it's preferentially incorporated into the calcite. And that means the drip water is getting heavier progressively. The more calcite you take out, the heavier the drip water is. And so you get a more positive calcium isotope values as you lose more calcium from the system as the FCA gets lower. Now, to quantitatively turn that into an indicator of PCP, we need to know exactly what that fractionation is between the dissolved calcium and the calcite. And there's not just one magic number. In lab experiments, that number depends on the growth rate. So I've shown two different possible scenarios here, depending what capital delta fractionation factor we assume, or if it's constant or not. But in general, this starts us out as having a way to calculate the PCP. All right, the other indicator on the right that probably we're all more familiar with because we've been talking about it for 2 decades now, is that trace element ratios of cations that substitute for calcium can often be good indicators of PCP, because the partitioning coefficient of magnesium or strontium or barium is very low. So as you precipitate calcium, you take out calcium more quickly than the magnesium. And therefore, as you start to lose calcium, the ratio of magnesium calcium in the drip water and the stalagmite goes up. So some of the uncertainties in this indicator are, well, we know that temperature affects the magnesium partitioning coefficient, the DMG. I've shown here 2 different temperatures about 8 degrees apart to show the magnitude of effect that would have. Sometimes we have to be careful about whether the bedrock is dissolving congruently. or if we just don't know what the initial composition is without degassing. Now for the trace elements, I'm going to show you a little shortcut to get around those. So classically, if you wanted to calculate, if you measured magnesium, calcium in your stalagmite, like you have on the x-axis in this graph, and you wanted to calculate how much PCP had happened quantitatively, you'd use this green formula up here, the Rayleigh distillation formula, where you'd use your measured magnesium, calcium in this stalagmite. And then you'd also need to know, well, what was the ratio of the drip water before it degassed, the initial magnesium, calcium, and what was the D, the distribution coefficient. Now, if you're going into caves like we are, we really take conservation seriously. So we're not breaking active stalagmites. We're picking up pieces of fossil stalagmites that maybe stopped their growth 100,000 years ago in some cases. We don't have any way to measure the drip water that formed that stalagmite before it degassed. We don't even necessarily know what the partitioning coefficient was, but that doesn't mean we have to give up and go home and stop using carbon and magnesium. So if you have a stalagmite growing for a long period and you assume that the lowest magnesium calcium that you measure in the stalagmite is the least degassed with little PCP, you can calculate something that closely approximates the Rayleigh FCA just by dividing your minimum magnesium calcium ratio by the one that you've measured in the sample. And so this red dashed line shows what that approximation looks like. It's not too bad. So you're just simplifying and basically using the measured stalagmite record to approximate the product of this D and the initial magnesium calcium ratio. And as long as the partitioning coefficient is very low, as it is for magnesium, this approximation is very close. So this is the approximation that we'll use in some further examples. Now I want to show you a head-to-head between calcium isotopes and magnesium calcium in 8 stalagmites from caves in northwest Spain. So we want to know, do these 2 different indicators of PCP give consistent results? So to first order, I'm just going to show you the scatter plots here where magnesium calcium is always on the y-axis and the calcium isotope ratio is always on the x-axis. And these are places where we've measured magnesium calcium throughout the stalagmite, but at 2 points of contrasting magnesium calcium, we also took samples for calcium isotopes that Chris Day has measured. And so I'm showing here for those 2 paired analyses, or for a few more in Gallia, what the results show. And this red arrow at the bottom just reminds you that PCP should bring about a positive correlation between both of these indicators. And in fact, we see in all the stalagmites that magnesium calcium and calcium isotopes are positively correlated. So to first order, there's agreement in that they're showing PCP at the same times. And I'll show you the same kind of plot for strontium calcium, where strontium calcium is on the y-axis and the calcium isotopes are on the x-axis. And here, this could be one of those little Sesame Street panoramas where, 3 of these guys are doing the same and one of them is doing their own thing, because in 2 of these 8 stalagmites, there's actually an inverse correlation between strontium calcium and calcium isotopes. So that's incompatible with a PCP control over both of these. I would suggest that in some situations, there are other controls on strontium partitioning, such as growth rate, which overwhelm the effect of PCP. So I'm not going to talk any more about strontium calcium as a PCP indicator today. Now, qualitatively, we show that calcium isotopes and magnesium calcium give the same results. But now we're going to look more carefully and see if quantitatively they agree. So in this plot, on the x-axis, I'm showing the measured magnesium calcium ratio throughout the stalagmite in all the points. And I'm showing some curves for the FCA that you would calculate from that. The gray curve A is if I assume that the lowest magnesium calcium I measured in the stalagmite has no degassing, i.e. the FCA is 1. And then I use that to calculate the evolution in all the other samples. The yellow curve B is if I say, well, my lowest magnesium calcium might still have a little bit of degassing. Let's say, 10% of the calcium has already been lost to PCP. Then you'd get this parallel curve a little bit lower down. Now these crosses show the FCA you calculate from calcium isotopes at the 2 points we've measured it. And you might say, well, but there's 8 crosses there and you only measured it at 2 samples. So each color for the cross is the FCA you'd calculate from the calcium isotopes, assuming a different calcium isotope fractionation factor from 0.66 up to 1.37, the highest fractionation factor that's been measured. We don't know in a fossil stalagmite which fractionation factor is right. So I'm showing you a series of plots where we can explore what solutions of fractionation factor and magnesium calcium behavior could be consistent and compatible between the 2 indicators. So here, this yellow curve B says one possible solution is that the calcium isotope fractionation factor is changing over time in the stalagmite. And so the FCA could be evolving over the stalagmite between, say, 0.9 and about 0.6. And in this way, the magnesium calcium and the calcium isotopes could give a coherent solution, this curve B. But this is, of course, not the only possible solution. So on the right-hand side now, I'm showing 3 other possible scenarios. This pink curve labeled C is a case where we assume, well, the fractionation factor of calcium isotopes is constant, and there's something that's causing the magnesium calcium to amplify. So if we just took a straight relationship with bedrock, it would follow this gray line. So we're going to correct for that change in partitioning in the magnesium calcium by forcing it to fit the calcium isotope data. So the blue curve is another possible solution, as is this green curve here that looks a lot like curve B. So the differences are what fractionation factor we assume for calcium, if we assume that the calcium isotope fractionation factor is constant, and if we allow the magnesium partitioning coefficient to vary. So for example, these colored scenarios here, this pink scenario to fit the calcium isotopes would require that there was a range in the magnesium partitioning coefficient in my stalagmite of about 30%, that it was systematically covarying with the magnesium calcium ratio. So, it would be great if we had one unique solution between calcium isotopes and magnesium calcium, but we don't. So going forward, I'm going to show you 4 possible scenarios for FCA from all the stalagmites that look like curve A, and then here C, E, and D, just so that we can explore these possible effects. This is just another example to show you that the same thing happens even when we have a lot more calcium isotope results. If we were to use curves that assumed no change in magnesium partitioning, they would come out like these gray curves, and the amplitude would be too big. There's no way that the magnesium partitioning coefficient can be constant in this case. It has to have considerable variation to match the calcium isotope data. And one question for the community is 2 to 3-fold variation in the magnesium partitioning coefficient with a higher partitioning at higher magnesium calcium, is that consistent and reasonable with what we know about how calcite is growing? And can we verify it? So there's some nice work that Jasper Wassenberg published 2 years ago in some monitoring studies showing this variation in magnesium partitioning coefficient with magnesium calcium. And this is, I think, an important area to follow up. What I'd just like to point out is this stalagmite here, it's only growing in the Holocene. So this magnesium partitioning coefficient variation is not just due to a temperature effect. So let me wrap up now where we are on the PCP indicators. So we have to admit, there's multiple solutions when we're trying to calculate the fraction of calcium remaining in in fossil stalagmites. And we see pretty big variations in the partitioning coefficients if we're trying to reconcile these two indicators, especially in the low magnesium calcium stalagmites. One possible solution for some of our high magnesium stalagmites could be that the magnesium partitioning coefficient is constant. So it may be that there's some ranges where the partitioning coefficient is strongly sensitive to magnesium calcium and others where it's not. And in the next step, I'll show, given this uncertainty, how much does it limit us trying to separate PCP and karst effects on the isotopes? I'll just show you one more caveat. I like magnesium calcium as a PCP indicator because we can measure it continuously in parallel with the carbon isotopes. So every sample we drill for isotopes, we can take some powder and measure magnesium calcium, or you could do a laser transect. But I don't think we're ever going to measure calcium isotopes at that same resolution and frequency. So when we do have to be careful with the trace elements is if the bedrock has multiple phases with strong differences in the dissolution kinetics. And you can tell this in monitoring. If you see big changes in the ratio of, say, magnesium to strontium, that's telling you that there are changes in the congruency of dissolution and that PCP might be biased by this change in dissolution. Some stalagmites have a lot of detritus. If your magnesium calcium is varying with the aluminum calcium, you got to be careful because the magnesium changes may not be driven by PCP, but by how much clay you're getting in there. So the second important issue is, even if we know perfectly the FCA for a stalagmite, do we know how to take that and sort of isolate the component that's due to PCP? And this graph here shows some possible evolution pathways for the carbon isotopes of Dripwater and therefore stalagmites from them as you start degassing and precipitating calcite, going from 1 to 0 along the x-axis. So this, let's assume these drips are all starting, at about -14 per mil. Equilibrium kinetics suggests that this rate of change here has a slope of about -5 per mil with the log of the calcium initial ratio. However, some studies suggest that maybe there's some kinetic factors that come into play, and maybe this relationship is a little steeper. Maybe with PCP, there's even more of evolution in the carbon isotopes. Now, most previous modeling has focused on comparing the evolution of carbon isotopes, not with calcium here, but with the DIC, the dissolved inorganic carbon. And there's been some fantastic frameworks for that, starting already with the work by Mullinghaus and Dennis Schultz et al. Here, what we're trying to do is evaluate relationships with the calcium, because we can have independent indicators for the evolution of calcium. And that's viable as long as the decline in DIC and the precipitation of calcium are coupled. So first, let's look at what happens in the equilibrium case, and then I'll show the experiments suggesting some non-equilibrium. So CAVECALC is a software developed by Owen and Day that integrates some of these calculations with isotopes and trace elements. And here I've shown how steeply do the carbon isotopes change with PCP for a couple of different simulations, in this case at different temperatures, going from about 25 to 5 degrees. Now, CAVECALC assumes not only that the solution chemistry is temperature sensitive, which we know it is, but it also suggests that the precipitation of calcite from DIC has a temperature sensitive fractionation, and that is still debated. Some experiments do not show that. So there could be about a 1 per mil difference, a little bit less, as temperature varies in this fractionation factor, but it also could be less temperature sensitive. For the rest of the talk, I'm going to use an approximation for equilibrium of about -5 per mil, because that's in the range of the temperatures in the caves that I'm working with. Now, some experiments, both in cave settings, tracking the carbon isotope of Dripwater, as it flows across a flowstone surface and loses its calcium, or as it does the same thing flowing down a ramp in a laboratory, suggest that 5 per mil happens sometimes, but often the carbon isotopes are evolving much more rapidly with less calcium loss. So these would be the slope as a histogram, a rough histogram, where the orange data are from Mickler et al. From in-cave experiments, and the blue data are from Hansen et al. In some cases, the slope is getting up to the range of -10 or greater. So today I'm going to show you a sensitivity experiment where we use a value of -5, a value of -8, and -11, just to look at how much that matters. So I'm going to show you a couple of examples of applying this correction now, where we use 3 different slopes for the carbon and where we test 4 different possible ways of converting measured magnesium calcium into an FCA. So for each data point, there'll be 12 possible outcomes. Now, so that's a lot of data, but we'll look at it in a histogram. And the first question I'd like to ask is, if we use a really steep slope here, like this -11 per mil slope, is there a risk that that overcorrects things? And does it give us unreasonable values? And the one place where we probably know whether a value is reasonable or not is during the interglacial periods. So we'll start by looking at the Holocene, saying, okay, if we use these 3 different slopes, are all of them giving us a reasonable range or not? And when I say there should be a reasonable range, if we look at the right-hand side of the graph, and I'm sorry that I flipped it, but the right-hand side of the graph is from Pataki et al., and it shows the carbon isotope ratio of the respired end member of soil CO2 in a number of different biomes, from boreal to temperate conifer to broadleaf to tropical. This is kind of the most negative that the soil CO2 could be. So if the most negative the soil CO2 could be is about -27 per mil, when you convert that into bicarbonate, you're somewhere in the 16 to 18 per mil range. And this suggests that we should not be getting values that are more negative than that for our corrected stalagmites. So this is kind of the limit of the legal window. On the left-hand plot, I've put a green bar, which is showing in this particular cave, what is the modern undegassed delta 13C of DIC and very fast dripping active stalagmites. So for 2 stalagmites here, Golda and Gallia, I'm showing the 4 possible calculations of FCA. And then I'm processing through with a 5 per mil, 8 per mil, and 11 per mil correction factor. And this is just a histogram of what the corrected values look like. So if you want to see what the FCA ranges are, there's a little inset here in orange. So the real question I want to ask is, if I use 11 per mil for any FCA estimate that's been calculated consistent with calcium and magnesium isotopes, I'm still within the legal window for both of these stalagmites. So I don't have any evidence for overcorrection. I can't rule out that really strongly kinetically enhanced fractionation is happening. We can also look, for example, there's some published data from Heshang Cave, and that also suggests that even using this extreme kinetically enhanced fractionation factor, we're still mostly within the window of what could be happening from areas with a high soil CO2 with this kind of respired isotopic ratio. So I know that doesn't tell us which of the 3 numbers are right, but it does tell us that all of them could be reasonable, and that these higher kinetically enhanced fractionation factors may be more consistent with what we expect the soil CO2 to be, at least in a very open system of dissolution. We can do the same kind of exercise for the last interglacial, assuming that like the Holocene, it's warm, a lot of vegetation, high CO2. And again, for this series of 4 stalagmites, yeah, this very high fractionation factor of 11 per mil, it is permissible and possible. So in the figures I'm going to show you next, I'll show you some time series covering the penultimate termination and the most recent termination. And in that, I'll still show you these 3 fractionation factors and the 4 scenarios. So this is one of my favorite stalagmites, Garth, named after country singer Garth Brooks. And the x-axis is showing age. So I'm showing you now the time series of the carbon isotopes. And this beige record at the bottom is the ratio that's measured in the stalagmite, which has both a PCP and this soil epikarst component in it. And then I've shown these 4 different scenarios for how we estimate the FCA to correct it. This little orange inset shows what each of those scenarios are. And the solid line in each case is if I correct it with a slope of -8 per mil. So the green and blue are these 2 scenarios corrected with a slope of -8 per mil. And then the shading around them is taking that same FCA scenario and saying, well, what if it were 11 per mil? And that would give us a bigger correction, so a more negative carbon isotope. Or what if it were only 5 per mil? And that would give us a less correction, and it would put us down closer to the measured ratio. So if we just step back and say, okay, we have the uncertainty from these kind of 3 possible slopes, these 3 to 4 different FCA scenarios. What is similar and what is different, and how do they change the record? In this case, the main change with respect to the measured record is that if we take out the PCP component, we get a little bit more slope between the early deglaciation and the emergence into the interglacial. So this suggests that temperature and soil respiration are continuing to increase as we come out of the glacial. Whereas if we just looked at the raw records, we might say, it was already warm very early in the glacial and it never got any warmer. And we see this intensification of the slope in all of the corrections, but it's more pronounced in these 2 scenarios for FCA here. And another way to look at that on the right in these gray bars, for each of these scenarios of FCA and for each of the slopes, I plot on a scale of 0 to 1, how well does the corrected record correlate with the original measured record? And if the correlation is 1, basically the correction has not changed the trend in the record. And as the correlation decreases, it means that we're changing the record more by taking out the PCP effect. So overall in this stalagmite, we're not changing the trend very much. So overall, the correlations between the records, they're still relatively high, because essentially the only thing we've changed is this, because this is the only place the magnesium calcium is really varying a lot in this record. Now, this is a scenario where already right away, if we look at this plot of correlation as a function of scenarios, we see that correcting for degassing has made big changes, because already the correlation coefficients are dropping below 0.5 and even down to 0 in the final correction. So we can look at this the same way. This is age. This is a stalagmite called Bellatrix. This is the carbon isotopes. These are the 4 scenarios for doing the correction. And here we see the measured record is relatively flat. And there's a very strong correction to give a strong increase in soil CO2 consistent with strong warming as you come out of the deglaciation. So this induces a strong trend coming out of the deglaciation and introduces a slight trend coming in. So this period, instead of being a peak, actually turns into a local minima. And another example, not especially well dated, but we know it covers the deglaciation, where the carbon isotopes that we measure are almost flat, and it's only after taking out the PCP effect that we see a trend. And I think this stalagmite must have grown in a sweet spot where in the measured record, the PCP effect is completely balanced by the increase in soil CO2, precisely because increasing the soil CO2 makes it more prone to PCP. So if we were just going to compare the first two records I showed you, Garth in purple and Bellatrix here in red, and I've put the dates underneath so you can see that the offsets in them, they're really not age uncertainty, they're differences. This upper record is showing the magnesium calcium, and that, as we predicted, that looks very different among the two records. And the record below is the measured carbon isotope ratio, which is still modestly different. So the R for this is 0.56. But if we look at the corrected record, now the bottom panel is showing the corrected with no PCP component. The overall trend in these records becomes much more similar than it was in the measured record. And in fact, if we do a 2,000-year bins, the correlation coefficient is going up to almost 0.9. So this would be the hope, that we can move towards harmony by separating out this more chaotic PCP effect, which is not necessarily reproducible among different stalagmites, and getting at a climate soil epikarst signal that is more related. So the final example I'll show you is one from the Holocene, where I'll show you the time series. This again is a record. If we look on the right, if we look at the correlation coefficient, we haven't done a lot of correction to it. But the small amount of correction makes a difference in how we see the deglaciation. So the age scale is on the bottom from 16,000 years to present. The brown record is the measured carbon isotopes. And it would suggest that there's no real change in the soil epikarst processes and the temperature between the Bowling Alarad and the Holocene. But all of the possible degassing corrections put some slope in this because of evidence for changes for higher PCP in the Holocene. And those lead to a difference in the soil component between the Bowling Alarad and the Holocene. So it imparts this slope. And the black lines in the background are the adjacent sea surface temperature records from the Iberian margin. They too do suggest that the Bowling Alarad was not quite as warm as the Holocene. So this is making the record more coherent with independent temperature records. So let me sum up at this point so we have some time for discussions. CAVECALC is a great tool, but we should remember that probably the -5 per mil slope that it would use to separate a degassing PCP component could be the minimum slope. So it's a great first place to start, but we can't rule out that the slope might be steeper. So it's probably worth a sensitivity test with a couple of different slopes. I think deconvolving the PCP can make the records more similar, especially when temperature is controlling the soil PCO2. And just a caveat, well, I think this can improve the trends. It's still going to be very hard to get the absolute carbon isotope ratio the stalagmite had before degassing. So harmony is easy. Unison will be very difficult and maybe not realistic. In my viewpoint, the biggest issues we still need to solve in order to get more reliable approaches to deconsolve this, first of all, we have to interrogate the magnesium partitioning coefficient and how much it's dependent on the magnesium calcium ratio itself. This first observation that Wassenberg showed, because that's amplifying things, and that could lead us to overcorrect the records if we don't account for that. The other open question, right, what is the rate at which isotopes evolve with progressive degassing? You know, is it that we're trying to find out whether it's everywhere -11, or will there be some situations that will have values closer to equilibrium and some farther from equilibrium? And right now with just kind of 1 or 2 lab studies and I think 1 published field study, we need to get more data to really understand that. If you're really, really nervous about doing an explicit correction for the PCP effect on the carbon isotopes, at the very least, you can screen. So this is an example for Garth, where I took my measured carbon isotope curve and I've just color coded it by the magnesium calcium index so that I can see, okay, here magnesium calcium is not changing much. So this is probably not affected by PCP. Uh-oh, here there's a big change. I can't assume that this is giving me the same trend as I was before in soil epikarst. In contrast, this stalagmite, well, there's times where it's pretty similar. I can probably assume that the carbon isotopes in the soil epikarst system really were more negative here than here. Another way to look at this is to plot the carbon isotopes versus magnesium calcium and say, okay, within this narrow window of magnesium calcium, PCP hasn't changed much. And so all of this trend is likely due to soil epikarst processes. So my final slide, I wish we were, at number 1 right now, where I could show you, yes, we have the answer, we know how to do this, and we can get, one magic answer for the right correction. We're not there. So then what do we do, right? Up to now, maybe some people have even left their carbon isotope measurements in the drawer, not published them. We don't talk about them because it's hard. But I think we're getting smarter than that. And so I would propose a middle ground where we can start to assess the possibility to distinguish the PCP and non-PCP components in a transparent way where we show the assumptions that we're using. And at the same time, we start working in a synergized way to constrain the factors such as magnesium partitioning and the slope of carbon isotope change during degassing that are the important unknowns in this process. I have an Excel sheet that is very simple. If you want to try to do these corrections with some of your own data, just send me an email and I'll send you the Excel. We're hoping to submit a manuscript with this data and this discussion within the next month or so to Climate of the Past, where you have further opportunity to give some feedback. And I hope there's time for questions and discussions now. Thanks a lot.
Thank you so much, Heather, for sharing these very interesting results. So we would open it for questions. Are there some questions somewhere?
I can I can start while people are collecting their thoughts. I know this is about maybe the second time I've come across the talk, and it's still a lot to take in. Although I know it's complicated, but then just hearing it the second time, it does get easier. So I'm glad it's going to be on YouTube to process all of the information. Thank you also for pushing the carbon isotopes. I know we've been pushing it for a while, and it's more convincing when we're able to say that we can do something with the data to understand it more and things like that. I just wanted to ask more that with SciSal version 2, so we will be having MGC, SRCA. We will hopefully have more carbon isotope records than we've had before. What would be your sort of wish list questions? Like if you did have this database with global records covering different kinds of regions and soil patterns and vegetations and time periods and forcing. So what would be your wish list?
Well, I think one of the exciting things is that as both carbon isotopes and some trace elements, or maybe miraculously some calcium isotopes come into the database, it might be possible to look beyond just the carbon isotopes that we see to look at what it might have been initially. Because I think on a global scale, I mentioned that glacial times are going to have less PCP because the soils are have lower CO2. But you will also see that potentially on a spatial scale. So in areas where there's cold temperature and you don't have such a high soil CO2, it may be common to see stalagmites that don't have a lot of PCP. If you go to these super warm, wet areas in the tropics where there's high CO2, you may have a lot of PCP always overprinted on that signal. And that's going to exactly invert or counterbalance some of the trends that you might see if you could magically sample spatial variations in the d13C of the DIC and Dripwater before it degasses. And so if in the database interrogation, people can keep that in mind and start to look for both factors, I think that will be really interesting. Or to start to look at, if there's a fast drip sites, to say, okay, let's just skim off the fast dripping ones in the tropics and warm areas and see in that subset, do we see things that correlate more with land use? Because it's possible, just like this stalagmite I showed with the flat glacial, interglacial measured carbon isotopes, it's possible that some of that is happening on a spatial scale, because where the DIC would have very negative ratios in the tropics, the PCP is high and it's pushing it down. And it may also be very interesting to look at the correlation between magnesium, calcium, and carbon isotopes, what it is before and after a degassing correction. So I know that the degassing is much more complex, and this whole generation of detailed models that's come out of Dennis Schultz's group, reminds us of that. So what I've shown today, it's necessarily a simplification, but it's trying to bring what's possible into what's realistic with the data that we actually will have from any stalagmites we pick up in the cave. The best we can hope for is some approximation of FCA from the magnesium calcium. And we know it can't be higher than 1, it can't be lower than 0.2 or 0.3, or the stalagmites wouldn't grow. And if you have a range in magnesium calcium in your stalagmite, you probably can fit pretty well where that must be.
Cool. Thanks, Heather.
I'm guessing the silence is mostly terror and not complete approval, but
I think Vanessa has a question.
Yeah, I have a question. Thanks for the very nice talk. And I just wanted to ask if you could, I don't know, repeat how you estimate the FCA, because you're just using the initial magnesium, like the estimated initial magnesium calcium, and the sampled magnesium calcium and the partition coefficient, but
I don't even use the partitioning coefficient.
No?
I don't need the partitioning coefficient.
Oh.
This is what's beautiful about the simplification. So you're just saying basically the minimum magnesium calcium that I measure in my stalagmite, it's the product of the partitioning and the initial in the drip water. And so I'm getting those two variables together with one measurement. Go ahead.
Sorry, because I'm wondering how because I thought you should, or you would also need they would like to simulate the calcium concentration, or like how the calcium concentration decreases, because you can, from your initial magnesium calcium, you could reach your samples magnesium calcium in a faster time if you have a stronger difference between the initial calcium and the equilibrium calcium, because you would have more precipitation just in time. That's
yes. So this is the slide that just shows the formula that I use. So it's just the minimum magnesium calcium that you measured in your stalagmite divided by the magnesium calcium for each sample. So in the Excel sheet that I can send anyone who wants, I plug in my column of carbon isotope data, my column of magnesium calcium data, and I just have a little formula that says, what's the minimum in the magnesium calcium column? And so in this example, it's 2. And so then I'll take that minimum and say, okay, that's the FCA of 1. And then I use that to calculate for every other magnesium that I measure. I'm still using that minimum value of 2, and then I'm using the sample. And it works for magnesium quite well because the partitioning coefficient is so low that this exponent is basically, taking the inverse ratio, right? But the other question is, how good is this minimum? So there could be scenarios where your stalagmite is, universally heavily degassed. And then you don't have much variation in your magnesium calcium. And then I could say, perfect. If you don't have any variation in your magnesium calcium in your stalagmite, probably PCP is constant and your trends are robust. And so a correction is not so important if you don't need to change the trend of your carbon isotope data. If you have a lot of variation in magnesium calcium ratio in your stalagmite, then it could affect your carbon isotopes. Then if you apply this correction, the risk that you could have is maybe your lowest measured magnesium calcium doesn't have an FCA of 1. Maybe it's already lost some due to degassing. And that's why we do some sensitivity analysis with that assumption. So in the spreadsheet, one of the things you can plug in is you could say, my minimum measured magnesium calcium, is that 0 degassed, or is it already 10% degassed, or is it already 85% degassed? And then do the calculation with that assumption. And so when I'm showing in some of these later graphs with the corrections, you can see in some of the assumptions I'm doing, I don't assume that the lowest magnesium calcium is giving me an FCA of 1. I think, here also. So for some of these, I've said, okay, my lowest magnesium calcium is 0.9, and for some I've said it's 0.7. So I'm checking those different possibilities and showing, what effect does that different assumption have? What's the difference between assuming that, it's the lowest magnesium calcium is hardly degassed, or if it's already quite degassed, so that would be the difference between the red curve and the blue curve. And then we can see, yes, it makes some difference, but it still is giving a trend that's quite different from the measured ratio. Does that give a little bit of clarification, or is there something I've missed in trying to answer?
Was already nice clarification, but
okay.
I was wondering if the as said, your how fast, or in which, after how many seconds of degassing you would obtain your stalagmite magnesium calcium ratio. It would depend on how much carbon calcite precipitation you would have, which depends on the initial and the equilibrium calcium concentration in the solution. And I'm wondering, how much variation would come from that.
So for estimating the FCA, it doesn't matter how long it took to get to that FCA, right? You're just looking at the final result. The magnesium calcium is 6 instead of 2. It's lost 2/3 of its calcite. Now, if it's warm, it could have lost that very fast. If it's cold, it might have taken longer. But you're just looking at the final outcome in the trace elements, not how long it took to get there. How long it took to get there, how fast it's happened, that is maybe more important for the carbon isotope slope. And so it may be that the faster degassing is giving slopes more like -11, and there could be scenarios with really slow degassing where you're getting slopes more like -5 per mil. Yeah. And I think we need a lot more people measuring, across flow stones to see in cave settings if there are some controls over that, right? Or if, so I spent a long time, honestly, thinking this -11 was too much. And I thought, yeah, in my caves, it's not going to be -11. It's going to be like CAVECALC. And we did measure down one flow stone and we got -11. It's not published yet. And that was a relatively low saturation. The initial calcium was only 55 ppm. So it told me, well, it doesn't have to be really extremely oversaturated to get this kind of kinetic enhancement.
Mm-hmm. Nice, yeah, thank you. Now it makes sense how you say it. I have to think about it again, but
yeah.
Thanks a lot.
Yeah, no, it's not really fair. I've been thinking about this for 3 years, and you guys get half an hour. That's why I'm really, really glad that Sisal does the YouTube videos.
Yeah.
And then you can look at it and then, in a week say, wait, Heather, you said this, but are you sure that was right? And yeah. Somebody who knows a lot about this, Jens.
Yeah. Thank you, Heather, for this nice, your nice thoughts and for sharing it with us. But I haven't also get anything, I think. So you need to change the D of the magnesium calcium, right? But I haven't understood how you're measured or where your 2 points came from.
Okay,
is this from the same speleothem and some parallel transects, or
this is where we have 2 independent indicators of PCP: the calcium isotopes and the magnesium calcium. But we don't have as much calcium isotope data. Like, we didn't measure calcium isotopes at every point. Mm-hmm. So I have roughly 2 data points for each sample, and those are these crosses. So the reason I say I think we have to change the magnesium partitioning coefficient is that in almost all the stalagmites, if I have a constant magnesium partitioning coefficient, I can't get the same FCA from magnesium calcium and the calcium isotopes. So here, if I want to use the calcium isotopes, I would like to say that this Rayleigh formula, or this line should pass through crosses of the same color. If the calcium isotope fractionation is constant, right, these lines should go through lines of the crosses the same color. And I can't do that unless, as in the panels of the right, I change the partitioning coefficient. So if I want the magnesium calcium estimates of FCA to be compatible with the calcium isotope ones for a given calcium fractionation factor, like this pink and blue, then I would have to assume that as I increase the magnesium calcium ratio of the stalagmite, I've also got, say, a 30% increase in the partitioning coefficient of the magnesium calcium. So I either have to change the magnesium partitioning coefficient, or the other solution, like this green line, is if I have almost a constant partitioning coefficient, but I assume the calcium isotope fractionation factor has changed across the stalagmite. But there's no solution where both the magnesium partitioning coefficient is constant and the calcium isotope fractionation factor is constant. And we know there's reasons that both of them can vary. So the calcium isotope can vary with growth rate. I've shown scenarios where I don't make it vary hugely. Jasper presented this pretty interesting data suggesting that the magnesium partitioning could increase as you have a higher magnesium calcium ratio of the calcite. And that's a really clear trend in his sort of high magnesium calcium stalagmites. And we can't quite see that in the scatter from his lower magnesium calcium stalagmites. And I think that's really, really important for us to investigate further, to see, is this kind of systematic relationship? And then especially, you know, what we need in this stalagmite here, are these reasonable? Yeah.
I see. Yeah. Okay. Yeah. Thank you. So I'm very keen on reading the discussion paper and climate fast then, so to really get a clue on what's going on.
Okay.
Thank
Good.
you.
Then we have a question from Stacy.
Thank you. I actually, well, it was very similar. I was just gonna, thanks Heather very much for your talk. I was just thinking about why you were choosing to change the fractionation factor on the magnesium calcium as opposed to the calcium isotope fractionation factor, because it seems like there's quite a large range in those 4 points that you show. So I was just wondering if that could also be the case that you just mentioned. So.
Yeah. So I thought it would be rather scandalous to assume the entire range of variation in calcium isotope fractionation factors that's been seen among all calcites. So I kept a rather small range, like the range seen, for example, in Wet et al. Among different modern stalagmites growing under different drip sites. So I just remind people that calcium isotopes have been applied as a quantitative PCP proxy so far only in cave systems where they've actually measured the fractionation factor in modern farmed calcite under that same drip. And so there, you know, for your stalagmite, you know the fractionation factor, but it gets much more challenging when we're picking up, you know, fossil stalagmites that aren't actively growing now, and we don't know what it is to start out. And you know, to change that, I've also made the assumption in most of these that the stalagmite, the calcium isotope fractionation factor becomes more negative. So down in these black points, as the stalagmite growth rate gets higher. But I haven't used stalagmite growth rates per se. I've just said, well, where we have a higher FCA during cold periods of low saturation, it's also often where the growth rate is slower.
Okay, thank you very much, Heather. So I think with this, we will close this session. And it will be on YouTube streamed. And also Heather already said that you can send her an email to get the Excel sheet, and we will keep in touch. Thank you very much for joining.
Thanks everybody for coming.
Thank you. So bye-bye.
Bye.